Okay, well, thank everybody for coming. What we're going to do today is I put a bunch of slides together, not so much on each component that we have. Our ignition systems is basically a lot of different troubleshooting practices. Um, this will be the first session for today, and then next week we're going to get into the Ultronic 3 and the Ultronic 5. Show you how to set it up, some overhaul part of it, and we're going to talk about what we have changed over the last few months on upgrading to 3 and 5. And we're going to mention that a little bit today, but just because I have a few of them on my slides, but we'll get in more depth of it next week. And then the following week after that, we're going to get into the DET, our detonation device, along with the VSM, even though it's not ignition related, that it uses the same type of sensor. So we're going to handle that 3 weeks from now. And then the following week, we're going to, we've talked about what we want to do on that. So after we get through this presentation today, if there's stuff out there that that we touched on during this presentation that you would like to know more about, please send me an email. My email address is michael.porter@horbigger.com. On stuff, maybe you would want to learn a little bit more about the CPU 2000 or maybe the 95 or the XL or just anything that you may be interested more in, that we can sort of customize the fourth version of this around the needs of our customers. So otherwise, we're going to put something together one way or the other on it, but we would like to be able to make it worthwhile for our customers out there. So. Also, I want to give you an update as far as today, because it's been asked many times, do we have another way of programming our CPU 2000 because of the serial port? And I can announce today, yes, we do. We do have an adapter now that if Ken Swilly would like to kick in and maybe a little comment on it, he just downloaded the software today and tried it out. And from what I hear on the email, it's worked extremely well. So I'm not sure exactly when that will be available, but we have worked all the bugs out of it, and we do have an adapter now that will plug into a USB to any type of a USB computer, and you'll be able to program the 2000s now. So anything you might want to add to that, Kenneth? Or?
No, I mean, like I said in the email, it worked flawlessly, exactly like Gary said it would, and that's about
great.
it.
Again, I'm not sure how we're going to roll that out, but we do have one available now. Okay.
Hold on one second. Folks, as folks that are joining late in the discussion here, if you would, please go ahead and mute your microphones and mute your video. As I said here, if there's questions that need to be asked, we'll have a session at the end of the discussion. And also, if you need something's not clear, you'd like to ask a question while Mike and Paul and Matt and the rest of the guys are reviewing the material, just go ahead and press your space bar. But otherwise, it really helps us a lot with the bandwidth and also to keep the interruptions to a minimum here. If everybody can just mute both the video and the audio inputs from their side, so much appreciated. Thanks.
Okay, what we're going to start
Hey, Mike.
out with is yes,
Mike, this is Matt Traina, real quick. In terms of the rollout, I figured I'd just chime in. So yeah, a lot of work was done for that adapter. It's pretty difficult to maintain stuff that's been around for 20, 30 years. So trying to get well, you wouldn't believe that some of the IT hurdles were some of our biggest challenges. But anyway, we were looking at boards that we can buy that we were going to 3D print cases, because we're anticipating maybe a couple hundred of these that will be needed maybe over the next year or something, just to get them out there. Then it'll probably be pretty slow after that. Once you have in your hands, you just kind of reuse them. But we actually found one that we could purchase already in a case. So we've got those coming in. We should expect to see them soon. And then we'll just verify that we can use those in the same way. So we're just trying to feel out if we can just buy ready up, things that we can ship with a cable, put it in a box, or if we need to actually make our own case for the adapter board that we're buying. So more to come on that, but thanks, Ken, for the feedback. And over the next couple weeks, you'll hear more about how we can get some. I don't want to call them production because I guess they're not really. I mean, they'll be sold, but they're not a product per se. They're more of a tool. But yeah, those will be coming out in the next few weeks as something that will get in your hands that'll be readily available. So any questions, just feel free to email me. Most of you that are dealing with these already kind of know my email, but I believe it comes out with the PowerPoint information anyway. So if you have any questions, just get a hold of me or Mike or Mr. Bell or Paul McHenry. We'll be able to take care of you. So thank you.
Okay, thanks, Matt. Okay, let's get rolling here. Okay, I'm going to start out with the basic stuff as far as what we're trying to do with our ignitions. And hopefully everybody can see this video. One of the things I've come across in my Ultronic years, and also I analyzed engines for 20 years. So, and one of the things that I have found that a lot of people don't realize on a two-cycle engine, that there has to be a positive inlet pressure. Make the exhaust go out the exhaust. As you can see from this demonstration here, this is would be like a chainsaw, a dirt bike, snowmobile for us people up north. But even in this case here, you got to have some type of positive pressure either being generated from a jet assist turbocharger, from scavenging cylinders, from a gear-driven blower. All this stuff has to be in the process to start with before you can actually start the engine. And what I'm going to do is stop this slide here and then work it on through. See, even on this case here, we're pumping air from the crankcase into the combustion cylinder. You can see this has a little flopper valve here, so this would be more like a chainsaw or like I say, a snowmobile or something on that line. But it has this area here, acts like a compressor, and it forces air into the cylinder to push out the exhaust. Now, all of our big engines, our big Coopers and our two-cycle engines, they do this with some type of either gear-driven blower that's connected to the crankshaft, like the GM VCs have a big gear that actually spins that blower almost up to 6,000 RPM from an engine that only runs at 300 RPM. And then, of course, after it gets the air into the cylinder and gets the turbocharger working, and then it's got a hydraulic coupler, like a torque converter on an automatic transmission, that they drain the oil out of the converter, and then the converter free flows. So after the turbo gets running, it pushes air through the blower, but it's free flowing at that point to get it into the cylinders. But and the reason I brought that up is because I've run across a few people before, blaming, of course, the ignition system, but come to find out we weren't making any air. And this doesn't require much. Normally it's only like a half a pound or so to push fresh air into the cylinder to push the bad gas out of the cylinder. So, and then as we get into more and more emissions, we put in catalytic converters downstream, or we're modifying the turbos to blow more air into the cylinder. But the turbo itself or the exhaust piping, because either maybe the catalytic converter, the muffler, or even the casting of some turbochargers are restricting the flow of gas or exhaust on the hot side. So even though we can pack the air into the cylinder, we can't get rid of the exhaust because of how it was manufactured, maybe back in the 30s or 40s. So this is something you have to consider when you're doing setups where you're trying to make either a lean burn engine by blowing more air into it, or even trying to start an engine. You got to make sure all these components are working to make air before you throw fuel at it, or even before you make put an ignition to it, so you can start it off. So So anyways, that's the 4-cycle. I mean, it was a 2-cycle. I apologize. So even in the 4 cycles here, we've got air being drawn in from the piston, acts like a suction pump, pulls fresh air in. We compressing it, fire the plug. We're making power. We open up the exhaust and push it out. So even in that case there, since we're trying to pack more and more air into these engines nowadays to make them leaner, we've got to take in consideration of the porting going out the exhaust, if it can handle the excess air that we're building and excess power we're building in the cylinder. And this, I've got an example for it was a White Superior where the engine ran for years at a really, really light load and did make a lot of air. So they pulled the turbo off, took it in, had it modified to make more air at a light load. Well, that was done 20, 30 years ago. And now the condition has changed with the pipeline. So now the engine's running more at a full load. And this had no wastegate on it. It had butterfly valves on the intake side. So to make this engine run, we had to pinch off the butterflies so they were just barely open, like even maybe like an inch open. And then we got the thing under a load, the turbo would go into a surge. And we never could figure this out because we didn't at the time realize the turbo was modified. So we fought that for a number of years, and then we brought in a Superior guy that was an expert in that kind of stuff and looked over the situation, and we ran some numbers on the turbocharger to the company that overhauled it, and so, oh yeah, we modified that for that reason. So that's the other thing. I mean, all this stuff, you've got to make sure that the engine can flow good air in and air out. Another example for this was one they put a brand new panel on, new ignition. They went through, and this was on a diesel valve engine, and they dumped the program into the panel that was from a Cooper engine, and modified it a little bit, but they were trying to dump 12 pounds of fuel into the intake or into the fuel for light off, because that's about what a Cooper starts off, 12 to 13 pounds. Well, a diesel valve, we found out, starts out like a half a pound. Same with a White Superior. Hardly any fuel's required to light this thing off to get it going. And what eventually happened to this, they had a brand new muffler on it, a brand new overhaul on it. And when they were trying to get it started, of course, I got called in because I thought it was an ignition problem. And what eventually happened was they started backing the fuel off on the engine and got down to that sweet spot, to that, half a pound, 1 pound, where it lit off. Well, unfortunately, they had managed to fill the whole exhaust system with natural gas. So when it lit off, it took the muffler right off the side of the building. So little things like that, you've got to realize that every engine has its own capability as far as what it needs and what it doesn't need to get it to light off, and it's not always the ignition. So anyways, enough of the basic stuff here. So one rule of thumb is, we've talked about this for many years, that air is considered an insulator. So air, it takes, when you run in a lean mixture, it takes a lot more energy to get that spark plug to fire off, and we're running into that more and more with these lean burn engines. And of course, fuel is a conductor, so if you got a rich mixture on some of the older rich burn engine, it doesn't take a lot of energy to light that off. So, and this gives you an example at the bottom down here, where if you were just firing trying to make a spark across a couple electric bars, that you can probably throw a spark about an inch long, and then you put it under pressure, and with about a 15,000 gap, it can take anything from maybe 8K to 40K to get the thing to light off. So, and why is that? Well, these are some of the conditions that you run into, where this is an article, was in Champion Spark Plug magazine many years ago, giving an example of different conditions. As their compression pressure increases, it takes more energy because you got more lean air in there to get the spark plug to fire off. If you fire the engine close to the top dead center, it takes more energy, and basically that's because there's a higher compression in the cylinder at that point. So by advancing the ignition, sometimes you can get it to light off easier. The faster the engine goes, requires more energy because, again, you've got more pressure in the cylinder. The load, more load on it, more pressure in the cylinder. The electrodes on the spark plugs, the hotter they get, the easier they are to fire. But unfortunately, if you get them too hot, they start melting the material on the plugs, and you get shorter plug life. So we try to run cold plugs, but to do that, it requires more energy to do that. So, and one thing I have come across over the years is, for example, like a Stitz plug. For whatever reason, I think because there's more metal in a Stitz plug, it normally requires more kV voltage to fire one over maybe a Champion or something similar like it. So another thing we come across is the condition of the connector on the spark plug. You know, the ends on it, as they get old, they start rounding off a little bit because of the metal and stuff breaking away. And the smoother that gets, the harder it is to light that off. And if you ever had a chance to visit with Charles from Champion, he actually does a demonstration where he has this rod that he holds in one hand, and then he's got this electrical probe in his other hand, and he's trying to get sparks to jump across a rounded rod. And it's fairly hard to do. Well, if he uses a square bar, it jumps across fairly easy. So same type of deal with a spark plug. So, and of course, the gap, that's sort of a no-brainer on that. The wider the gap is, the harder it is to get the spark to jump across. Coil polarity, that was sort of explained to me by Matt a little bit there, that you've got the central electrode normally runs hotter, so it's easier to give up electrons through a hotter surface than it is a cool surface. So that's so if you were to have inverse polarity on a coil where you're trying to fire it from the ground strap internally on it, that would probably end up taking more energy. So, and of course, back to the last one there being your air-fuel ratio. Of course, the leaner it gets, the more air you've got in it, the harder it is to get that gap to jump across. So, with our capacitor discharge systems, we store energy in the capacitor. We use a electronic switch that we close, and we flood the coil with that to get it to spark. We ionize the gap, and then after we jump the air across the gap and starts the plug itself arcing, it doesn't take a whole lot of voltage to do that. But of course, the wider the gap gets, the more worn the plug is. Like I said earlier, it takes more energy to do that. And with our standard capacitor discharge ignition, you only have so much energy in that cap. So if you use up a majority of it just to get across the gap, there's not enough left there to actually arc the plug for any long period of time. Here's an example of that. So you see my little mouse here. This is how much energy it takes to ionize the gap. So after we get the gap, where we got electricity going across it, it doesn't take a whole lot of energy to maintain the gap, but the more to maintain the spark. Whoops. But the more that plug wears out, the taller this gets, and our rise time extends even further out. So between here and here, pretty much all stays the same because of the capacitor. But if we burn up all of our energy by coming down here and getting a real wide rise time out of it, we only end up with a little bit of a arc time, and then of course the rest of the energy can't withstand the gap, so it just ends up going back to ground. So that's very important, the idea that you got to use a type of plug that can withstand that, or you got to start out with a fairly tight gap in some cases, so you can get maximum life out of the plug on it. So, but then again, if you get a real tight gap, you'll get a spark, but you won't get enough energy coming off the spark to light off the mixture. So, and this is an example looking at a capacitor being charged here on the primary side. It discharges. You can see where it ionizes plug of the gap, and then you can see the actual arc time, and then you can see the ring down time, and then you can see the capacitor build back up again, charged, and then dump again. And now this is happening 4 times, like on our CPU 2000 per revolution on a 2 cycle. So, and one thing you notice with our systems that we normally don't allow you to go into energy level 3. Well, some of the reasons behind that is because we're doing this so quick. The time it takes the capacitor to recharge itself, where it can fire again, in some cases there's not enough time, so you can't get the capacitor to charge all the way. So that's the reason we normally only allow you to go to energy 1 or energy 2 on it. And you can't get to 3 on it. So our different types of ignitions we have. Our basic one are our mags that we've had for years and years and years. They're self-powered. They've got a generator inside on them. We've done away with the points that they had many, many years ago. And it's self-contained. You don't need any outside source. You can put it on any engine anywhere and fire it. So again, we're going to talk about more about this in our next session next week. So, but I wanted Matt to highlight a little bit on what we've done over the last few months on some of the upgrades we did on the Ultronic 3 and 5. So if you want to add a little bit to this, Matt, without giving it all away for next week.
Yeah, sure. I think most people have seen the brochures and the mail that has gone out from Dave Bell. But essentially what we've tried to do is, we've all heard that we're trying to take the technology from what was, 40, 50 years ago now into some of the modern age. So this has been updated to use solid state switches, more precise timing, and everything is, again, self-contained, backwards compatible, but we've been able to eliminate the pickup coils. We've been able to reduce that process in manufacturing and update with all the latest technology that's been available only within the last few years. So that's a picture of the 5 being installed as a full length back cover. You can see on the bottom there that the 3 connections are where your connector would go, and then there's a high energy magnet on the front cover side, and that replaces the old 8-pole rotor magnet, and it's allowed us to have a little bit higher energy. And so what Mike was talking about earlier with the storage cap, we've been able to increase that and actually get a little bit higher energy and duration out of it. And we'll talk about that pretty in depth next week. In terms of next week, the other thing I want to cover as well, that as you can imagine, I wasn't around when this was developed. So I've kind of gone to school on a lot of this for gear ratios that maybe you guys have all dealt with. But if there's anyone newer out there, or you're not really building these up in terms of just replacing parts but not thinking about, why everything is such a decoder ring in troubleshooting, in terms of RPM, cranking speed, 2-stroke, 4-stroke, we'll cover quite a bit of that next week. So yeah, stay tuned.
Okay. The only thing I wanted to add to that, because of the few people out there that have these already, one of the questions when they're putting together, and I know we'll cover that next week, but I wanted to throw that out there with our little Hall effects that we have here, that if you're going to set this thing up, it doesn't really explain it real well in the instructions, but at the 12 o'clock spot up here, I think I've got it right, unless it's upside down, is where you need to line up your wheel at there to get it to start out with time there when you put the gear on. So
yeah, the 12 o'clock position is the A, number 1, just like we do for everything else. So that's primary A, number 1, where you want to line your magnet up when you set up the timing on these. Yep.
Okay, thanks, Matt. Now this is our old Ultronic 1 that was been around for a long, long time. I think it's a cool ignition and how it actually operates for its technology back then. They're still out there running pump jacks and stuff. So, and it's fairly a simple thing to hook up to. I mean, you got the big flywheels on the Ajaxes and stuff out there. In this particular one, we're firing only 1 cylinder, and it's got 2 magnets on the flywheel, and it's got the pickup here. And the first magnet is that indicating magnet to tell the ignition to get going, and then it's going to fire on the second one. So, and then down here, we're going to fire. We're actually firing a 4-cylinder, but we're actually only firing it twice, because as you can see here, these coils are wired together. So this coil and this coil here both fire at the same time. So that's what we're going to discuss here in just a little bit about a wasted spark on it. And then you get these two here firing at the same time. So when this one here is fired on the compression stroke, this one here is firing on the exhaust stroke. So, but fairly simple. It's a little self-powered deal that fit with the old mag was. And just the idea of the pickup technology back when they did that was sort of incredible for its time. So anyways, that's our first one. Then we get into our disc trigger fired ones. There's our DISN, our CD1s, our CD200s, our CD200Ds, our CD200VS or EVSs, and then our newest NGI 1000. So again, these all fire off either a disc, or if you wanted to do on a camshaft, or if you wanted to drill holes into the flywheel and then fire on the exhaust side of a 4-cycle, then it allows you to do that. So they're real accurate, not as accurate as our mag pickups on the flywheel, where we're counting gear teeth or holes in the flywheel, but and there's also with a few of these where we can actually fire in between discs on there too. But they've been real dependable, been around a long time, and fairly easy to set up. So this is the wasted spark that I wanted to discuss here a little bit. You'll see this a lot on irrigation pumps and stuff along that line, or non-turbocharged engines, where they actually are firing the plugs twice, or they fire 2 cylinders at the same time. One's under compression and one's under on the exhaust stroke. But they've been doing it for years. Normally, the reason you do not want to do it on a turbocharged engine is because turbochargers engines normally run high oxygen in their exhaust. So if you do get a misfire here, and you've got excess fuel and into the exhaust, and you fire it, you may end up getting a backfire into the muffler on that. So, but anyways, give you an idea how that works. That it actually does, and a lot of the cars did back in the 80s, maybe early 90s, ran this same way. I found that out by mistake when I pulled an engine for my daughter, and they had a distributor, and I ended up going to the crankshaft, and it had on the crankshaft had these notches cut out on the crankshaft, and I got educated on that a distributor engine wouldn't work on a crankshaft. So, but anyways, both had the coils that were packed coils, and they fired 2 cylinders at the same time. So this is what if you were going to do, this is a CAT. I think it's a little 6-cylinder in that they put a wheel on the camshaft. You can see the pickup right here. This was a modification done by one of our distributors, and this is sort of a little drawing what that would look like on the inside. So we either had little magnets here if it was a Hall effect, or they would be notches cut out, or in some cases they even stick bolts here, and then of course that would pick that up and fire the timing. Of course, there would be one of these would be a index if it was like 1 + 6 or something like that. Those who didn't know that. So, and then of course our most accurate ignition system we have out there are ones that we come off the crankshaft with, that are either gear teeth or holes in the flywheel. Because as you know, an engine doesn't run at a perfect RPM. That every time you load a compressor cylinder, and some of them could be as high as 1,000 horsepower, every time that thing pushes gas, the engine slows down. Not that you can really see it on the tach or RPM or like that, but it's just the idea that it's going from like no load to picking up like 1,000 horse on some of these bigger engines. So the engine slows down. So when the engine slows down with a mag pickup on the flywheel, it can sense that. So it keeps the timing within about a half a degree accurate compared to the old days when you were running magnetos and everything ran off a gear or off a chain. Every time that engine had a little surge or all those gears in there would back up on the gear deal there. So you'd had to run the ignition sort of loose to make sure you didn't get into detonation on it. Well, nowadays you can push the ignition fairly tight because it's so accurate that it's a big improvement of what it was when the engines were first built back in the 40s. So, and this is the pickup set up on it here, and you can see the little gear teeth or the holes in the flywheel here. And these would probably be for the reset. I'm not sure why there's two of them here, but the most likely the reset pin would be over here. And then you also notice that this pickup's over here. And normally, I mean, there's a lot of people who do that, but normally myself, I don't recommend that because this flywheel or crankshaft moves back and forth. It gets hot, it expands. So when you've got a pickup like that, and you're only running like 10 to 15,000 gap on it, and this flywheel is moving back and forth, there's a possibility one, it's going to misfire, or it's going to not see the reset and then shut the engine down, or two, it's going to go the other direction, and the bolt that you're counting on hit the end of that thing and ended up snapping it off. So, and then on the next slide, this is a thrust bearing, and this is one out of a car, of course, but inside these big engines, they have these thrust bearings on the crankshaft also. So, and they normally run probably around, I'm guessing, 10 to 15 thousandths clearance in there. But as these start wearing out and that crank moves back and forth, that will affect that pickup on that. So something to keep in mind if you're having these mystery shutdowns where the engine may run for weeks or months, and then you get maybe a real hot day and like that, and all that metal looks extremely warm. That it could be because the crank itself or the flywheel itself is actually moving out there. So something to keep in mind. And you can get this on our web. This is explains a little bit about our mags, how much energy they put out. In this case here, they put out around 18 volts peak to peak, 9 volts as an average. And then we also have some dials built in there, some Xeno dials, to keep you from not having a lot of energy coming out of it, so it won't actually cause an arc if the wire itself has a short in it. So although we sell it as a intrinsically safe pickup with our systems, I'm not sure if we actually advertise it that way to be used elsewhere, because if you get people with analyzers and stuff along that line that are buying mag pickups to put on the flywheel to hook their analyzer to, they always talk about having to be intrinsically safe because when they connect it, well, ours, you can connect it why it's being used, and it won't cause a spark on it. So again, this information is in our underneath the accessories. So, and now we're going to talk a little bit about our crank reference ignition systems. And of course, that would be the 95, the 95 EBS, the CPU 2000, and the XL. Again, I mean, like I said, we can have the most advanced ignition system, but if it's not set up right, if it's not grounded right, if the engine's in poor condition, if you have a crappy air-fuel ratio control on it, the ignition system's not going to fix those problems. So, and I've got some examples here of stuff I've come across over the years that problems we've run into that the ignition system has got blamed for it, but it was caused by something else. So, this is on a Clark engine. As you can see, this particular cylinder here is running almost like 950 to 1,000 pounds at top dead center. And you can see the ignition timing was probably around, I don't know, maybe 10 degrees or something like this. I don't remember. So this is pre-ignition on the cylinder. And this engine was running, as you can see, this is another cylinder. It wasn't running that well, but it was making lots of air. It was not detonating. It was just purring along, basically. And then they ran an analyzer on it, and we ended up getting this cylinder. And actually, this cylinder, the Keeney valve was so hot on this cylinder that the pressure transducer got stuck on the Keeney valve. But you can see here, you can see the fuel valve when it opens and closes. As soon as this fuel valve closed, you can see this thing light off and take off. And it actually reached peak firing pressure before it got to top dead center. So it had a problem, but just looking at the engine or listening to the engine, it didn't have any indication at all that this was going on internally. And unfortunately, if this was to left run long enough, it could have busted a connecting rod, could have broke a crankshaft. But one of the things that that you got to be aware of on that. So now this one here, again, it fired roughly around 10 degrees. You can see it lit off, come off compression a little bit, a compression pressure, then lit off. So this would be except for the idea that it was very badly air-fuel ratio mixed on it. It was doing everything it was supposed to. As the intake port or exhaust port opened up, you can see where it starts blowing down here. So even though it was a bad running deal, it's still to the point where it wasn't going to destroy anything compared to that one. And this is overlaying all the power traces on together here as a parade. So, and you can see this one here like that. So we got extremely nervous after we started downloading the data on this. And having to see this in here. So again, I mean, it was running rough, and they were talking about the ignition system may have been misfiring or stuff along that line. But in this case here, this had nothing to do with the ignition. It was all internally. So we pulled the engine apart, and we ended up getting the piston out. And then we found out, see the piston here got heated up here, and it actually cracked. So we had an indication that this possibly could be a spot where it might have been glowing, causing a pre-ignition part to light that fuel off. So that was the only thing we found in the cylinder at the time that we thought may have caused the thing to light off. So they put a new piston in and got it up and running again, and seemed to correct it. So this is a timing trace on it. They were multi-striking it, as you can see. We're only reading 3 of the 4 strikes on it, and you can see these here where you've got a lot of energy here, and as looks like that's probably where it lit the cylinder off, and then it had not a whole lot on the next few strikes. Well, this one here had hardly any ring down on it, and it was taking a lot of energy to arc it. Well, it was arcing when it was like 900 pounds in the cylinder compared to these being probably around 200 to 300. So an indication, if you are looking at it with some type of analyzer or oscilloscope or something along that line, and you do see stuff like that, I mean, you may want to look a little bit deeper into the engine or to see that there may be something else causing that. So this wasn't the same engine, but this was another engine that was pre-igniting, and you can see that it actually destroyed the ends of the spark plugs on it. I think this was like GmbH Cooper engine that, again, had another hot spot in the cylinder. I mean, one example is that I was at one station and they had just put in new spark plugs, but they had one of the operators there. He was taking the spark plug and dipping it into a Never Sees can, and instead of just putting a few drops on the threads, he was actually dipping it into the can. And it was a 12-cylinder engine. He did one side, and then the other guy did the other side. Well, this thing ran for like 3 weeks, and they just couldn't get it to balance, or they were having problems with it. So the analysts come in and analyzed it, and they got on the first cylinder, and they saw that it was pre-igniting. So, and the operator there said, well, how do you know that? He said, well, because I could take the spark plug wire off and the engine will stay running. And so he did. Not that I recommend doing that, but and what they found out with that was the never cease that was on the end of the spark plug dripped into the cylinder and made like little BBs spots on the cylinder, on top of the piston and on top of the head. And we feel that that was probably what was causing this thing to light off, because it ended up burning up 3 fuel valves. Um, it just did a lot of damage to the cylinder heads and stuff on that, all because of, believe it or not, never cease. So something to keep in mind. Wiring practices. This seemed to be our biggest problem that we have with a lot of our ignition systems is the wiring itself is not properly installed. So want to make sure when you are wiring stuff in there that, I mean, I know it's pretty handy to put extra wire in boxes and stuff so we can use it maybe at a later date or something, but we normally recommend to run them as short as possible to try to keep down some of the noise and stuff on it. And then we recommend running our pickup cables in separate conduit, because we really don't want you running them next to the primary wiring or maybe high voltage wiring or like that, because it's going to pick up that sparks or spike in the wiring, and then count that as a gear teeth or extra gear teeth, and then maybe cause to shut the engine down. So, and even our harnesses, we don't recommend you pulling on the harnesses to try to make them fit on that. So the example you see down at the bottom there, even though it's hard to see, this is one that we worked on for about, oh man, it must have been 3 to 4 weeks. This was a KVS, and it was firing, it was 2 plugs per cylinder, and it was firing 1 plug on the compression stroke, and it was firing the other plug on the exhaust stroke. And I mean, he picked it up with the analyzer, and I mean, not knowing what was causing it, we started pulling boxes, the output module, replaced it, and I finally got to the point, because I said couldn't be there for a little while, so I recommended him shutting off the one that was firing on the exhaust stroke. So we get there, and I even recommend them to ring the cables out. So they went through, like, say, L here on this cable on this end, and then L on the other end, and of course everything rang out good with a ohm meter and stuff, and we really couldn't figure out anything wrong with it. Well, I got looking at the connector, and normally underneath this groove here, the first pin, I believe it's an N here, so it's like L, N, M, or something on that line on this first one. Well, this particular cable got twisted 180 degrees. So what was supposed to be up here was down here. So by doing that, we actually was firing, and this was a 32 output module. So by doing that, we were actually firing 180 degrees off on the second cable on that. How that happened and how they managed to get it exactly 180, I have no idea, but it ran that way for who knows how long. So it's very important that when you are getting into stuff like that, to check little things like that and make sure these cables aren't twisted inside the connector on it, and because of stuff like that. So the next thing is as far as our grounding connect. And as you know, we bombard you guys about grounding, and we just never enough grounds on it. But so it gives you a little bit of an example here. If you do have a junction box and you have our ground wires coming into the box, we recommend that you put them on different lugs in there. And the reason for that is because you're grounding this to a metal box, and hopefully this junction box is grounded to the engine block somewhere along the line. But if you start stacking these wires on top of one another, and for whatever reason this box may get loose or whatever like that, it's a lot easier for that voltage to go down copper line than what it is to jump through these boxes in the engine ground. So what we find out on it, and sometimes it takes a while, like if you got the P lead up here and you got everything dumped on that, well, that you'll force that energy down that P lead back into our output modules, and then you'll burn the boxes up. So we do highly recommend, make sure when you do the junction box and all the other grounds like that, that you avoid trying to stack them on top of one another. And I apologize for the slide being a little bit blurry here, but you can see the P lead coming out here and where it's going to ground here, and then these other grounds are coming in from the coils, and they're grounded. Oops. Grounded, and it basically shows you that they're grounded in separate spots on it. So that's what we're trying to point out here, along with the idea at the end of the conduit, we would recommend grounding them out here. The idea is to get that energy into the engine block because it acts like a big capacitor more than trying to push it back into our electronics, causing problems. So another thing we highly recommend is if you're going to do any welding on this engine is to disconnect these cables on it, because 9 times out of 10 when they're welding on an engine block somewhere or some of the piping like that, they may have the ground on one side of the engine and they may be welded on the other side, and this electronics don't like that. So take the time to disconnect these connectors so you don't get any backfeed from them welding machines into these boxes. And this is on a 95 where you got the J wire coming out, same type of deal here where they have them separated in the J box, so they're not stacked on top of them. Some advanced features in our modern ignition systems. And compared to our old CPU2 and some of our other older models like that didn't have the diagnostics, we've come a long ways with that, and then we're going to continue in the future with more stuff that are in the works, I'm thinking. So, but I mean, the secondary on it now, where we're looking at the voltage demand in there, our reference numbers, that we can alarm when they get high on it. So it'll tell us that we have a shorted plug, or not so much a shorted plug, but maybe a broken wire or a spark plug that's wore out, so we can schedule maintenance on it. And then we can trend that, not so much with our systems, to the point where if you took this data, dumped it into a panel somewhere, and store that over a period of months on end, you'll end up seeing what I call the sawtooth effect. And I've got a sort of a slide to demonstrate that, where as the demand numbers climb up, they get to a point where maybe you have 18 to 20K on your plugs demand, and you replace the plugs, and then you'll see that demand drop off again. Then over a period of time, you'll see that start climbing back up again. I mean, sometimes by just going in there and looking at the reference numbers from time to time, it doesn't really help you any if you didn't know where you was when you started. So it's nice to be able to document this somewhere and store this information, and then over time watch this the plug roar away, or maybe the wiring get banned and stuff along that line. And then you can put alarms in it to the point where if you are looking at maybe with an analyzer and he's telling you got about 18 or 20K on it, that the plugs need to be changed, you can look at your reference numbers and say you may be at 120 or 130. So you can put an alarm in there, so the next time those plugs are in that same condition, you'll get an alarm saying, okay, I may be at the 18 to 20K. It's time to change the plugs out. Another feature we offer also is we can control the voltage going into the primary side. So if you got a fresh set of plugs, nice flat surfaces, a small gap, you don't need a lot of energy in your capacitors to jump that gap. So why throw a lot at it and prematurely wear the plugs out? So we can back that energy off. We got 3 different steps where as a plug starts eroding and getting worse, we look at that number, and then we can automatically bump the energy level up to get longer service life out of your plugs. And then, of course, we also offer on the primary and a secondary side, whether we got an open wire or maybe a grounded wire, we can look at this information and determine how to fix it. So even along with our pickups, I mean, if you remember back in the old days, I would call it, where we got an ignition system or the engine goes down, and you don't know if it's a fuel problem, you don't know if it's an ignition problem, you don't know if it's a mechanical problem, but the engine goes down, and it's a pickup. And so the end, you fire it back up again, it runs for a while, then it shuts back down again. So, I mean, the old days we had no indication of what caused that. Well, nowadays with our our modern ignition systems, if you do get a pickup or a Hall effect or a reset pin that has some kind of problems, it will tell you, this is where you need to go to look, so it could be the gap could have widened up, or it could have got busted off, or the wires may have vibrated and shorted out into the conduit, but it doesn't tell you exactly what's wrong with it, but it tells you where to go start to look at. So a lot of time is being saved by doing that. So, and this is some of the pictures that you would get in this system. First one being gear teeth. I don't see any gear teeth, so either my pickup has failed or the wiring itself has failed. So then the next one over here would be your reset pin. Same type of deal. Pickup has either failed or wiring in it. So, and if for the 4-cycle people, we got our Hall effect. It's got to be in the windowing there to be able to see that for the pickup every other revolution, where it knows where it's on the compression stroke or not. So I've got a slide that shows what that looks like a little bit. So, but even the ring gear here, we do give you a little bit of leeway on that, and I'm not sure if that's gospel or not, but normally if we're doing it with one of our demos, normally about 3 teeth or 3 degrees either direction from where the set point is, it will shut itself down. So if you have it on a ring gear and you end up snapping off one tooth, it's going to throw the timing off a little bit, but it won't shut the engine down normally. Normally you got to bust off a handful of them before it actually shuts you down. So, but then again, it tells you where to go look for it, where to go look for the problem at. So now this is an illustration if you were looking at with an oscilloscope, and again, this is would be the Hall effect on the gear teeth, and this isn't exactly right because it would normally be more of a peak in here, but just to give you an idea on that. But the main thing I wanted to point out here was with the Hall effect with the big magnets we have, and the cam running slower, you usually get a pretty big windowing for the Hall effect. But what you can see where this reset pin is, it's pretty close to where this Hall effect ends at. So if this 4-cycle engine, if the cam chain in it starts to loosen up, or even the idlers in it that keeps the tension on the chain runs into a problem, there's times where this could actually, or possibly, move around enough where this windowing here would actually jump over to this area and it'll shut the engine down. It will also, give you an alarm that's missing either a reset pin or missing a Hall effect. But these are the kind of things that you got to look out for when you do set these up. That you got to make sure they're in the middle here somewhere, not on the ragged edge here. So because you could run into problems, and it could go on for months or years, or it could be maybe a real hot day when the engine oil is extra hot like that, or it's got a more of a load on the chain or something like that to cause that to do that. And it would be a really hard thing because you'll look at the pickups and you test them and they test well, so you don't think it's a pickup deal, and you replace the wiring on it, and so it's an internal hardware mechanical deal on the engine itself. So something to keep in mind. Also on our reference numbers on it, the first one up here is we have the engine average, and we're flagging H here being lower than what the engine average is. And then we got high from engine average, and we got L telling you that whatever's going on with cylinder number L, that it's higher than normal on it. So, and this is looking at cable number 1. This would be a 32 output ignition box. And you can see the engine average is 125. And this particular cylinder is running around 132. And then the coefficient. And the coefficient tells you how stable the spark is. And normally they'll run around anywhere from 0 to maybe 3, possibly 4 at times. But normally there's a pretty small number. So when you start getting up to around 9 to 10, there's a problem here. And whatever it is causing this cylinder to be, I would say, extremely higher than what the engine average is. So you do see this on your screen, you see numbers like that, there's a problem somewhere. Either this thing is arcing to the head somewhere through a bad secondary wiring, or maybe there's a jet cell problem, or but something's causing this thing to demand more energy to spark, and it also when it is sparking, it's not a very stable spark. So this is good data to look at to troubleshoot problems while the engine's running. So, and then of course no secondary spark on K. That's just telling you that maybe the wire has fallen off or something's causing for a really high demand on the secondary on its stairs. Of course, this is a no-brainer here on cable 2. The primary has shorted on cylinder D, the firing order. So, and this could be just a small spot in the insulation on the wire that shorts against the conduit once in a great while. So this may be something that's very intermittent that comes on or off. May be hard to troubleshoot, but normally if you dig into it, you'll find normally a little black spot that has built up on the wire on it. So, of course, the primary open, that means that most likely the wire has come either disconnected somewhere or it's has broken somewhere in the conduit. So, in our latest version 2.1, we also offer these graphics in it. In our 2000s, and this is basically telling you, looking at all the numbers at the same time, and it gives you an idea, like F here is running a little lower, F and U is running a little lower than everything else is, and then second one down here is looking at the engine average, and this is giving you the highs and lows of the engine average. So if you do see something like that, most likely there's a problem with this particular spark plug on this one. Same down here. So. This is the coefficient here. So this is, again, telling you how stable the spark is. And in this case here, there's 2 cylinders here, or at least 2 coils on this engine that are extremely high. That, again, could be a worn wire once in a while arcing to the head, or a plug may have carbon buildup on it, causing it to misfire off and on, giving you an unstable spark. So really good indications to go look for a problem on the engine before it turns into something worse. So, and this throws a lot of people off, because I know we have a lot of people out there that looks at their reference numbers and they say, well, they hardly ever change, and it's useless information to me. But this is a graph that I got from engineering a number of years ago. That shows you under light conditions, like if you put a new set of plugs in, you're probably running somewhere into the 8 to 10 kV range in there. So from like 10 kV to 15 kV, there's not a lot of movement in here. I mean, you're looking at maybe you're running around 105 in this case here, up to maybe 110. So if you're setting your boxes up to use the data off this information, sometimes you got to set the numbers fairly close and then watch that change a little bit over time. A lot of people put them in, well, they'll start out maybe at 100, and then the next one's going to be at maybe 130, and then maybe 160. Well, there's a possibility, the engine conditions that is, the type of engine that is, that it may never reach that high. So you sort of got to custom program your numbers in there for how the engine is set up. So. And a good way to do that is when you, if you do have an engine analyzer guy there, and he's collecting data with his analyzer, and he is looking at numbers, 15, 20K, then you can set your boxes up for the alarm limits to be, gives you an indication that you're in that same condition. This is the sawtooth effect I told you about. We had a customer that put this into his PLC, so you can see here with a fresh set of plugs here at the beginning, and this also had pre-chambers in it that can see as the plugs start eroding that the numbers start coming up on it. Then at this point here, it was a new plug change, numbers were dropped back down again, and over a period of time they started wearing out again. In this case here, they had a problem with one of the check valves in the pre-chamber head. So you can see where this check valve ended up screwing up, causing the cylinder itself to run really rich or really lean, one or the other. and then cause these reference numbers to jump extremely high on it. So it's a really nice troubleshooting tool to have to utilize those numbers. So this is some data that's been collected over the years. Why is it so important to have a really good firing ignition system? So this is some testing that was done by some different parties. Again, back in the old magneto days when you had a lot of chain slop and gear slop, it was not too uncommon to see the timing move around, 4, 5, 10 degrees. 10 degrees maybe exaggerating a little bit, but anyways, this gives you some testing they did by the engines under the same load at the whole time here, and they moved the timing 20 or 5 degrees. Actually, they moved it less than, because this is peak firing pressures on it. So at 15 degrees after top dead center at peak firing pressure, the peak firing pressure is like around 900. By backing the timing, advancing the timing a little bit, or take it back, retarding the timing a little bit, pushing it close to the top dead center, you can see, though, this engine's under the same load now, but the peak firing pressure had dropped off to about 650 pounds. So you can imagine what that did to the fuel supply pressure going to this engine. And in this case here, it possibly maybe could have ran into detonation because it's not carrying a good load anymore. So with our new ignition system being really accurate, we're able to push the limits to these, so we can, come up to push right close to where detonation would be, because we don't have a lot of variation in the timing anymore like we did in the old days. So you could save fuel on that, but get better emissions and stuff out of it, and keep a tighter ignition curve on that. Now this was another test they did on a Clark, a TCV 20-cylinder engine, 2 spark plugs per cylinder, open chamber. This was not a pre-chamber engine. And what they did, they wanted to find out by shorting out one spark plug, not the whole cylinder, just one spark plug in the cylinder, what it would do for fuel numbers and efficiency and stuff. And as you can see, even though one spark plug was still firing in cylinder number 1 left, the other one was shorted out, and you can see that the fuel rate went up almost 2%. The energy efficiency dropped down to 1.38%. CO went up, and the NOx went up just by shorting one spark plug. So, give you an indication of how important that is, that to try to eliminate misfires from that. Now we're going to get into pre-chambers. I've run across a few customers over the years running into issues with their pre-chambers, so we're going to go through that here a little bit. So pre-chamber is basically, it's a chamber where the spark plug screws into, that's in the main cylinder. Oops. That we dump raw gas into, and then we light it off with a spark plug. And instead of having a little bitty arc in here trying to burn this big cylinder, we actually throw out a torch flame, so we can run the engine extremely lean and still be able to get it to fire off. So this is a little illustration here. There's a little check valve here, where as soon as that cylinder pressure drops below pilot gas pressure, gas will start flowing into this chamber. And gas actually flows in the chamber and actually flows out of the chamber too. So there's usually an orifice someplace up here to control how much gas is being flowed into it. So anyways, you got to have, it's very, very important to have the proper air-fuel ratio in here, because you can overfuel these things fairly easy. And I'll show you that in a couple of slides here. So, and I've run across that many times where, for an example, if you have a pre-chamber engine, most likely the ignition timing is going to be around anywhere from like 1 degree before top dead center up to maybe 4, possibly 5, because the flame front is so fast, where normally you would have ran the engine at maybe 8 to 10 degrees, you can tighten that up to almost top dead center now, because instead of trying to have a little kernel in it, you've actually got a big ball of fire going into it. So it speeds up that flame front extremely fast. So this gives you an indication here where we're mixing the fuel because the piston's coming back up. Now we're trying to force some air into this thing, so we got to like an air-fuel ratio in there. Then we're going to light it off, and then when it explodes, it's going to come out this porting in here. So, and this is an example of some of the Coopers, how they're set up here. You've got your check valve here underneath this 90-degree connector here, where you're dumping raw fuel in. Of course, is your spark plug. This is the diesel valve engine with aftermarket pre-chambers in it. And then what was sort of cool about this particular one is that this one here is in the water jacket, where you got to have seals top and bottom because water's flowing through this all the time. So there's a possibility if these seals break down, you'll end up getting Amitrol or water into the power cylinder from them leaking, or you'll see them leaking around the flange area here. What's sort of cool about this particular one, the way it was designed was this originally had spark plugs in it, and they bored the casting out on the head enough to get this chamber to fit in, but they did not cut into the water jacket. They put in I don't know, maybe about a 2.5 or 3 inch bushing, brass bushing in there to absorb the heat, so that the cylinder head itself, that was jacket water cooled, sucked the heat off this chamber without actually having water around it. So, and you can see on top here is the check valve to hold the fuel in. So, now this is another one, screw-in type pre-chamber, aftermarket. Screws into the spark plug hole. It's got two water lines here, inlet and outlet to keep the chamber cool. And then the line in the back here is a fuel line, and then down inside here there's a check valve in there too. So have become quite common over the years, but there's some issues times with those that they have problems with them off and on, but there's still a lot of them out there. And this gives you a little illustration of what actually happens. So you actually can see this is looking inside of a cylinder. And you can see the torch come in, and then the fuel lights off on it. So this is some testing that was done on it as far as the proper fuel that goes in these these pre-chambers. So in this case here, we had a baseline of 30 psi. This engine's under full load, and what they did is they started backing the pressure off on the pilot gas coming in, and you can see. The first one here, this is NOx down here, and then the second one is CO here. So you can see as they start lowering the pressure on the pilot gas, you can see where the NOx and CO starts climbing at 10 psi compared to 30. And then when they actually turned it off, you can see where it got extremely bad in there because the pre-chamber is not doing it anymore. It's just trying to fire off the spark plug. So, and then again, they cranked the fuel back up on it and got it, back where it was running good. So this particular engine, whatever it was here, it seemed to run extremely well with 30 psi going to it at that condition. So this is another example here of peak firing pressure. What they did here, same engine where they had 30 psi in here in the pre-chamber gas, and then they started backing the fuel off on it. And you can see the misfire start coming in, and the peak firing pressure dropped off a little bit. They got down to 10 psi. You can see where the misfires got extremely high, and then the peak firing pressure dropped even lower. And then when it got to 0, you can see that it basically barely runs. So it's really, really important to have that pre-chamber gas at the right pressure. And normally at light off, it requires almost nothing to get them light off on it. And in fact, I think some Waukesha's, they don't even turn the pre-chamber gas on until after the engine reaches a certain RPM. So, because of condensation and moisture problems they have with it. So, but I believe this was some big slow speeds that did this data. This is set up on a Cooper. This is on a Z330. This is a fuel inlet filter. Fuel pressure coming in, the regulator, and this is the line going out to the pre-chambers. This relay over here, this line here goes to the air manifold pressure. So as the air manifold pressure increases, we bias this regulator and we put more fuel in there. So this helps us over fuel in the engine. We can preset this regulator to give it just enough fuel to light the engine off. But then after that, we're relying on air manifold pressure. As it increases, we're going to keep on pushing more fuel to it. So one thing I've done in the past was a DSG 1682 gauge, where we were controlling pilot gas pressure with that. It was fairly easy to set up. Basically what we did was, after the engine got started, we started the engine on like a half a pound of fuel, and then we from there on up, we were bumping whatever the air manifold pressure was, we put it like a pound and a half more fuel to the pilot gas. And it did work. It was working extremely well. So one thing to keep in mind, though, is that when the cylinder reaches the pressure in the cylinder, when it gets below pilot gas pressure, it flows fuel into the pre-chamber. So this is why it's real important to give it just enough fuel, because as you can see from this illustration here, as soon as the exhaust valve or exhaust port opened, the pressure dropped off. The check valve, that holds back the pilot gas pressure, equalizes, and it starts flowing fuel into the pre-chamber. So this being a 2-cycle engine, the whole time it's on the intake stroke until the compression pressure starts building back up again, it's flowing gas into it. And on a 4-cycle engine, it's doing it all the way through the exhaust stroke, and also up on the intake stroke, it's flowing fuel into it. So because it's just got a check valve, it doesn't know electronically when to put the fuel in. It's all relying on differential pressure across the inside the cylinder on it. So this is a little drawing. I'm not sure how well you can see it from where you're at, but this is a drawing we did for that DSG 1682, and how we had looking at air manifold pressure coming into one part of the gauge on channel 2, and channel 1 was looking at the pilot gas pressure, and then we mapped that little curve in there, and then we were controlling an I to P, controlling the fuel regulator, differential pressure regulator, and that's how we were packing fuel into each of the pre-chambers. So now the other alternative is Horbiger has their pilot gas injection on it, where they can do it electronically, and they also can dump it in at any time, because of their pressure is like 500 psi on this. So thereabouts. So they're not limited to when the pressure is below a pilot gas. They can actually push that in there at any time. So it's a nice device to use. So okay, ignition coils. We're going to give you an idea how to test those, and how they affect. Where they're a step-up transformer, we're dumping in anywhere from maybe 150 volts up to maybe 400 volts, and getting about 40,000 volts out of them. So again, I think the things that affect that is the air filtration control, the load on the engine, of course the spark plug gap, spark plug condition if it's oil fouled or wore out, and the compression pressure, and how we put more demand over these recently because we're packing more air into the cylinders, because we're running them lean, so we're putting more demand on the coils. So this is a cutaway of our unshielded coil. You can see the primary on the outside, and then the secondary wiring on the inside. So if you ever get a chance if the virus ever goes away and you do get a chance to visit our factory, you can actually see these things being made. They have where they spin them up on this bobbin type deal. It's quite impressive. So, but then our shielded coils. What makes them a shielded coil, where they're explosion class 1 Div 2 coils, is the threading on the coil itself. So they're not to the point where they're sealed off, where they can't get gas inside of it to cause an explosion. They're designed, if they do get gas inside of it, and if they did have an arcing going on here, that would stay inside the coil part of it. And they don't necessarily have to be metal. Our coils for our XL system is made out of an epoxy, but they have that same type of connector on it. So they're still classified as Class 1 Div 2 coils. So what makes them not a Div 2 coil anymore is when you stick a regular wire in them, because when you put a secondary wiring on that's not shielded, that classification goes away on that. So this is how to test them. You have a voltmeter, and you hook to the primary side. And then in this particular coil here, the primary voltage should be someplace between on pin A and B, someplace between 1.9 and 2.7 ohms. So, and if you want to check the secondary, and this is for the blue coil, that's running like 0.2 to 0.5 on the primary side. For the secondary side, you want to make sure you get inside and make sure you clean the connector inside on it before you do this test, because of if it's got any kind of corrosion, it will give you a false reading. But it should range somewhere in there, and all this information is on our website. If you get into the, I believe it's our accessory page, and get into the coil side of it, you can get this data off this for every one of our coils that we. And also on the measuring the voltage on the secondary side. So that's nice. And that should run somewhere between 5,500 to 7,100. Negative side of the primary to the center of the electrode on the secondary side. So these are some tools that we don't offer them, but you can get them from different distributors for cleaning the inside of the towers. You have a lot of moisture problems, a lot of humidity in the air, grow that, call it the green gook in the bottom, and these are different things you can get in there with either a drill or something on the end of them and clean the towers and stuff on the coils. So checking your primary harnesses. If you get the opportunity where the engines are down, throughout the season, like if you're in a storage deal there and you pump gas in storage, but you have a pretty nice maintenance window on it, it's always nice to disconnect the cable from the output modules and get an ohm meter, and you can put the ohm meter in the pins and then go to the engine chassis ground, and that way you'll test the coil and you'll test all your primary wiring and all the connections from there to there to make sure they're in good condition. And you just keep on doing that on all the pins. This is a little chart that this one company put together. And you can see even this little change here, it's not much, but it was enough to flag some loose connections. After they corrected it, you can see where it was more in line here. So keep in mind, even though you see a little bit difference going on, it may be still worthwhile to go in there and make sure there's no corrosion, or make sure you don't have a loose connection, or a broken pin or something on that line. So RF, that's the one thing that sort of kicks us in the butt all the time. We highly recommend resistor spark plugs in all of our electronics. I've ran across a case with us installing a Gov Plus on an Ajax engine here about maybe a year or so ago, and they were running non-resistor plugs. They had non-resistor wires, and the plugs on these Ajaxes are a pretty good size spark plug on them, so it wasn't easy to find resistor plugs. So, but anyway, what was happening was our alarm and shutdown lights on our Gov Plus was blinking off and on at the same speed the engine was running. And I said, I think the spark plugs are doing this, because it was screwing the engine up as far as trying to make it run smooth. You can almost, because you know how noisy an Ajax is to begin with all the, the jumping around and stuff. It was almost perfectly it was perfectly in tune on when the spark plugs would fire. So, causing us problems, of course, with the the Gov Plus, and by replacing, we couldn't replace the plugs by putting a set of resistor wires on it. The problem went away. So again, it's something we run across a lot with RF noises. So we like, again, make sure you maintain your plugs, your wires. Try not to run really long secondary wires so they turn into an antenna. And try to keep all your connector clean, and make sure you got the grounds on that. So that would, extremely help. So this is one of our resistor wires. You can see the resistor in the middle of it now. All of our wires, I believe, have resistors in them of some sort. Again, if you're not running resistor plugs, or in some cases, it's maybe you might want to run both of them if you are running into these funny shutdowns and stuff. So safety leads, why are they safe? Well, I've got a video here that I'm going to show at the end of this presentation, because I've got to actually get out of it to get into it. So, but we actually have a video, and when I was down doing some work with Champion spark plugs here in Michigan, where we put a real high demand on the ignition, and we physically damaged the wire on the inside so it would spark. But we were actually getting internal arcing going on through the blue wire to the metal here internally. So even though it was happening, it was still safe, because the wire was we figured had broken down. The insulation is broken down. It shorted out to the metal here, and was actually arcing, but it was still contained inside this housing here, and so it wouldn't have caused an explosion. So, where if it was just a standard wire, if this insulation is broken down, then it would have arced out of the wire, and caused a spark. So I had one case where it wasn't on this end, but it was on the end going into the coil, where it was the insulation was blowing apart on all of them, and we were trying to figure out what was causing the wires to do that. It was all really hard carbon type material on the wiring and stuff. And what we found out was this was a high pressure fuel injection engine that they were multi-striking, and they were pushing the spark plugs up to around 25 or 26K all the time. So it found out that it was easier to blow through the insulation on the older wires and arc to the coil, because these were shielded stainless steel coils, that they found it found an easier path to go through the insulation and arc to the coil than it was firing a spark plug on it. So our recommendation was not to let the spark plugs run quite so long. So, and then our wiring. I know down south and a few other places like that, I call it the green gunk, builds up inside the coil towers. So got the option of using a dielectric grease to try to seal that in there and try to keep the oxygen and keeping the air out of it, so that helps a little bit. Or in some cases, we would recommend using maybe a stainless steel wire. That would be more corrosion resistance than maybe a standard copper wire. So something to keep in mind. Okay, well, now we're going to get into our high energy ignitions, like the EVSs and the XLs a little bit. I've done some testing on those over the years, and we got some test results. So this is basically a little bit on how the whole thing works. With a standard capacitor discharge system, you've got a capacitor that builds up here at the bottom, and then you dump the capacitor, and then whatever energy is not used to ionize the gap is going to use to arc the plug, and then leftover energy will just ring down. So, but again, normally when this is happening, the more energy it takes to arc the plug, the less energy you got left over to ionize the gap, the less energy you got to arc the plug. So that's good, but it has its issues. So with our high energy ignitions, what we're able to do, we've got a pretty good sized capacitor in there now it's basically stays charged all the time, and we have a high speed switch downstream of that that we can turn that coil on at very high speeds, so we can actually control the energy going out of the coil. And as you can see in this illustration here, we're actually, in this case here, we're actually turning this coil on and off multiple times, and we can actually increase we know when to do this, so we can actually increase the output of the coil by doing that. So that gives you a long, actually, we're not controlling the length of it, but we can pack more energy when it's actually arcing. So whatever energy it's being consumed to jump the gap, we've got a lot of leftover energy to keep the plug arcing. So, and it's, extremely helpful on lean conditions or, badly operating engines. And also what we can do with this, we can tune the spark. So we can turn it off and on. We can have long duration, short durations, and we can do a lot of custom stuff with this. So if you have an engine that may require a special type of spark, that doesn't fit into the waveforms that we've already created. I mean, we can make them tunable. So, and this is software that we do it with. So, they're done in the factory. So, and this gives you a little bit of an illustration here, where in this case here, looking at the coil output on it, we call this what we call flyback, or sort of useless energy. So, if we can turn off the capacitor for a short period of time when this is happening, and turn it back on again here, we can get more energy out of this. So, us doing that. So with the same amount of energy going in, we can increase the output energy by just being able to turn the primary on and off at really high speeds. So this is looking at a standard capacitor discharge where, again, the capacitor dumps. You can see it bleed off, and we're getting the arc, and then what's left over is the ring down on it compared to, and then we have our multi-strike that's been around. We can do it multiple times. But with our high energy ignitions, we can actually get some feedback there, guys. Okay. We can actually arc the plug, and then instead of the energy actually being bleeding off, we can actually pack the energy in there, as long as capable of doing that. So, and this is a case here where we're actually increasing the arc going in. So, and then we can do custom ones where in this case we basically had like a standard arc in it. We actually turned the voltage off, and you can see where it was ringing down a little bit, and actually stopped firing. Then we reionized the plug again, and then we continue to arc it again. And we actually, while all this was going on, we were pumping more energy in. A lot of capability, and we continue to improve on this as with our technology gets better. So there's just different examples. Now this is comparing a standard capacitor discharge, where you can see where the capacitors have bled off, and with the idea of overlaying a high energy ignition, where we actually arced probably 4 times longer what we did. And I know that people have played around with our XLs and have run across some cases where it has eroded the plug at extremely fast rates, but in other rates, I mean, it's done well. So this is an example here. This is on a GMV, a GMV engine where we had a little over 1,000 hours on this plug, and we gapped it at 20 thousandths. And after 1,000 hours, we pulled the plug out, and I think it was only like around 25. And this is a iridium and platinum type plug on it. So, but again, in other cases, we've run across where we've actually got indication where we've actually eroded the platinum metal on it. So, but if you're not aware of that yet, a few years back, we have redesigned our CPU XL coils, and what we have done is, let me see if I can help you a little bit. What we have done, we've rewired the coils, so when we ionize the gap instead of going really fast where we're actually throwing metal from one electrode to the other, we have slowed this process down a little bit, where it seems to has helped the erosion rate on the coils. So those are available. Have been for a couple of years. Now, this is some field testing that I've done over the last few years with the XL on a couple different engines. This one here being a KVS 412. This was modified with new turbochargers and intercoolers, and this had screw-in pre-chambers on it. And the problems they had with the pre-chambers were they were making water in the pre-chamber somehow. And of course, they're rusting and fouling out the spark plugs on it. So we had the opportunity to go in there with the XL. We unscrewed all the pre-chambers, put in a standard spark plug, and we got to do some testing on it. And as you can see, the results here, when we were packing in about almost 15 inches of air, the CO was running about 2.6, and the NOx was like 1.3 roughly. And as you can see with this illustration, we kept on packing more and more and more air into it, and we were able to get the NOx down to 0.8 grams. And as you can see, the CO went up a little bit, and that's normal. They were also running oxidation catalysts on this, so they were taking care of the CO through the catalyst on it. But and then as we pushed the air pressure up to almost 19 inches, you can see where the NOx came up a little bit, and you can see that the engine started getting a little bit unstable here. So we thought this was a good number here. So again, I think I got the slides here. That's not done on a standard KVS out of the box type thing. This had a added on intercooler here on it, updated turbochargers, wastegate control, and this particular one, they were actually dumping the air off, not the exhaust. And they had the pre-chambers on it that were screwed in them. We eliminated them, so we told them we could get the same emission numbers just by running a standard spark plug with our ignition, over the idea of having to deal with the maintenance and stuff on the pre-chambers. The next one we did was on a dealer valve. There's 4 dealer valves at this station. The first test we did was hooking the XL up, and we ran it in all 8 spark profiles. The first one being a single strike on it. And the numbers you're looking at here, the first one here is the NOx number. The second one is a CO. And then the third one here is the methane going out the stack. So you can see with a single strike, it was really misfiring a lot, and a lot of the methane was going out of the stack. So, and when we got into another spark mode where we were more of an extended, longer duration spark, you can see the rest of the testing better. So almost cut the methane in half. So the other thing we did was, since there's 4 engines there, 2 of them had pre-chambers on it, engines on it. They were the aftermarket one I showed you earlier in the slides. To do that conversion, that was like almost a $35,000 or $40,000 job. So we had the opportunity to go in there and put the XL on it. So what you've got here is cylinder number, or engine number 1 here had pre-chambers in it, and number 2 here had running a standard CPU 2000 with open chambers. Another pre-chamber here, and then the last one we had the XL on it. So you could see with the XL, we could almost compete with the pre-chamber engine. And this station had to stay below 10.5 grams of NOx. And with the standard 2000, even though after the turbos was modified, we were having a hard time doing that, especially even on really hot days. So they needed to come up with a solution for that. So, and the pre-chamber idea was extremely expensive. And we were able to get them down, I think, around 2 grams by just adding the. So it definitely improved at points. So right now, all 4 engines have the XL on it. So along they all run different profiles. 2 and 4 run the same, and then we run just a single strike on with pre-chambers on it. And I wanted to go to the next step on it, where I wanted to see if I could actually run this engine on one spark plug, because I was trying to talk them into putting pressure transducers, one of them, so they could actually look at the fuel or look at the compression pressure or peak firing pressure of the engine. There were no Keeney valves on this engine, so what we did is we shorted out the side spark plug. And how this, in this first reading here, we weren't reading methane here, but how you compare these numbers here, like 1 and 11 will be the same. 1 would be 2 spark plugs, and 11 would be 1 spark plug. And then 2 and 12 this would be 2 spark plugs. This is 1 spark plug. So on down through here. So we sort of proved the point where you could actually run this engine with a center spark plug on it without the side plug running on it, and still manage to keep some pretty good performance numbers on it. So they have never installed the pre-chambers on it, but the option was there if they wanted to. Not pre-chambers, but pressure sensors in there. Okay, that's got me up to question time, and I'm at about 3:40 here. So do we have any questions out there? Or anything you guys would like to add?
Questions for Mr. Porter? You can go ahead and unmute yourselves, or even just, as I said, just press your the space bar on your keyboard here to unmute. Yeah, that's good stuff.
Hey, Mike, this is Lester. I had a question. I was traveling today and I missed part of the program, but as far as like exhaust temperatures, if you're running too hot, is that something that you would advance the timing or retard the timing? How would that change the exhaust temperature?
Well, it depends if it's a 4-cycle or 2-cycle in some cases, but when you start pushing the timing, advancing the timing where it's firing close to the top dead center, that sometimes I believe that lower the exhaust temperatures, but when you start getting close to the top dead center, it pushes more heat into when the exhaust actually opens up. So I mean, for an example, not so much the exhaust temperature, but when you're starting up an engine that needs of some type of jet assist to it, we fire the timing sometimes 30 or 40 degrees after top dead center because you want the energy to go into the exhaust port.
Gotcha. Okay, that makes sense.
But as far as temperature-wise, I believe if you advance it, so you try to keep more energy in the cylinder, it would actually lower the exhaust temperatures, unless somebody wants to correct me on that. So. Thanks, Lester.
Yep.
Anything else, guys?
Anything else from Mr.
Again,
Porter?
like I said earlier, we're doing 4 sessions of these, and the next ones will be more of our equipment that we actually have. I just thought that we give you a little bit of a break because we've been really getting in depth on some of our products, and we're going to do that over the next few times. But the 4th one, we sort of leave it open for you guys to say, I wish I knew more about this, or I wish I knew some more about this, and so we can sort of custom build one for the 4th one. So, so again, feel free to email me or even Dave Bell or Paul or Matt, and we can, we'll try to put something together that is around stuff you want to learn on the ignition. So,
You
for
bet.
the 4th show. So.
Yeah, you bet. We definitely want to make sure that we have that 4th session lined out here. So don't hesitate to shoot us an email or a text or give us a ring, and we'll tailor those last 2 hours to exactly what you're looking for. So.
But hopefully this, hopefully you picked up some ideas from this. I mean, this is stuff that I have come across over the 30 years of me playing around with this stuff. Again, some of it may have been pretty simple and stuff, but hopefully it all helped. But
no, this is such a complex subject here, and there's so many variables here: the system design, the quality of the wiring, the application. this is a pretty complex topic with a lot of different possibilities and variability entered into it here. So what you're hearing from Mike and Paul and the rest of the folks here, this is years in the making, getting ourselves learning some of these little tricks. If you ask Tom Smith's been doing this a long time as well. This is a lifetime of learning in order to be able to share some of this. So we're glad that you spent the time with us here this afternoon. We look forward to seeing you next week. Mike, what's your specific topics for next week, for July 24th?
The next one's going to be the Ultronic 3 and 5. So
Okay. All right, good. Good stuff.
Hey,
and then the
hey, Dave,
third week will
before
be
we go,
go ahead.
sorry, I was on mute when the question was asked about the timing on the exhaust temperatures. I just want to touch base on that real quick. And it can be a complicated subject, and it depends on a lot of conditions. Again, lean burn versus rich burn. So I suggest, depending on what you're doing in your specific situation, if you want to, there's a lot of information out there, just even on YouTube and some other things. But I guess I'll just cover a few of the things that I know as the basics. And by no means am I the biggest engine guy out there compared to you guys that are out there installing and working on these every day. But the one thing Mike said is absolutely true, that when you're trying to start an engine, if you retard the timing, you'll push a lot of the exhaust, a lot of the spent energy out the exhaust, and that will help spool up the turbos quicker generally. It helps warm things up. But when you're running, the general rule of thumb, if you have way too high exhaust temperatures, there may be something wrong. It may be overloaded and you don't know it. So the first thing you want to do to bring your exhaust temperatures down are just going to be to reduce load. But if you want to, in the general rule of thumb here, I would say that you want to retard the timing because you're going to reduce your peak pressures and your peak temperatures. But what that's going to end up doing is, again, it comes back to load. So that's going to mean that you won't be able to carry as much load. But if you have more fuel or enough fuel is what you need, this is rich burn in general, then advancing it probably will, in some cases, can help you. In a lot of cases, it won't, and you'll probably start getting towards detonation. So just be very careful on that. Retarding the timing will always generally help you, because it's going to take you away from detonation. It's going to take you away from things that are going to harm the engine. And in general, it should help lower some EGTs because you're reducing the amount of work essentially that you're doing. But you'll probably then have to reduce load when you retard too. So if you're seeing EGTs that are climbing, or in this case, if you're saying they're too high or you think they're too high, I wouldn't necessarily look at the timing first. I would reduce load and then start swinging the timing at a reduced load set point to where you won't put yourself into detonation, and then see what the effects of the engine are. And then if you want to reload it back up and try again to see if the timing will help you. So if you're way out of timing, it'll probably have these effects on EGTs. But if things are supposed to be normal, I don't know that I would start there first. So I just wanted to bring that out. I didn't unmute myself, I guess. I thought I clicked the button, but hopefully that's helpful. There's the Joe Lepley's out there. He could probably go on for another hour about this, but I just want to touch base on at least the basics of what I can give you just in this short amount of time. So, okay.
Thanks, Matt.
Sure thing.
So next week, 3 and 5, and then as well as the new NG material. Bring everybody up to speed on that.